Okay guys, we'll be starting soon. Today we'll just keep the chat off because when we have the chat on, it's like a lot of spam and some of you guys don't like that. So today we'll be going over casework counting. You guys have like a basic understanding of counting, hopefully, and then we'll be using casework to solve all of our problems today. So we can start with the first problem right here. Bill is sent to a donut shop to purchase exactly 6 donuts. If the shop has 4 kinds of donuts and Bill is to get at least 1 of each kind, how many combinations will satisfy Bill's order requirements? And I'll give you guys a couple minutes to think about it. We won't be reviewing the homework this week because the homework is just like to help you. I won't really be like checking it or anything. It's for your own benefit, not for like you don't have to, it's not like required or anything. Okay, I guess we can start the problem now. So let's say that we have donuts 1, 2, 3, 4, 5, and 6, and then we also have the donut types are A, B, C, and D. Now, the donuts, we know that we have to have at least 1 of each kind, so we can say that like 1, 2, 3, and 4 can be A, B, C, and D, so that satisfies our requirements. And then we just have to find what the 5th and the 6th donuts are. So then this is where the casework comes in. So we will have 2 cases here, case 1 and case 2. So for the first case, we can say that 5 and 6 are the same kind of donut. There are 4 types of donuts, A, B, C, and D, so if we want 5 and 6 to be the same, there's 4 ways for it to be the same. Now, our second case will be 5 and 6 are different. When 5 and 6 are different, since we have 4 types of donuts, we have to choose 2 out of the 4 types of donuts. That would just be 4 choose 2, which is 6. And then when we sum it up, it is 4 plus 6, which is 10. So do you guys understand what like choosing means? Because if we don't, I can like go over that really quickly. Okay, so A choose B is essentially A factorial over B factorial times A minus B factorial. This is when we have A objects and we want to choose B objects, and the set is like not ordered, so we don't care about the order of the B elements, so it's just A choose B. If you guys like have any questions about that, I can expand on it. So are you guys good with this problem? This was like a really simple problem to just show you guys how casework works. Okay. Now we can move on to the second problem. How many 3-digit numbers satisfy the property that the middle digit is the average of the first and last digits? I'll give you guys like a couple minutes to think about it and then we can go over this. Okay, so we can start. So This time, instead of doing casework on like whether they're the same or different, we can do casework on the middle digit. Let's say that we have a 3-digit number A, B, C. So we know that the middle digit is B, so B equals A plus C over 2. We can rewrite this as 2B equals A plus C, and now we can do a casework on B. Let's say that case 1, B equals 1. So if B equals 1, we can have A as 0, 1, or 2, right? That means that, wait, let me write this as A plus C equals 2. So we can have A equals 2 and C equals 0, A equals 1, C equals 1, or A equals 0, C equals 2. However, we know that A equals 0 and then C equals 2 doesn't work because it's a 3-digit number, so the leading number can never be 0. So this is just 2 numbers. And then case 2, we can have B equals 2. We skip the B equals 0 case because if B was 0, then A and C both have to be 0, which is impossible because A has to be more than 0. So now if B equals 2, we have A plus C equals 4. Using the same logic as before, we can get that A equals 3. A equals 3, 2, or 1, so there are 3 numbers. A equals 4, 3, 2, or 1, so there's 4 numbers here. Okay, and then now we can go into the third case, which is when B equals 3. So A plus C equals 6. And then now there are just 6 numbers. And then we can go to case 4, B equals 4. If B equals 4, it's just 8, and then we can go so on until we get to case 5, B equals 5. Now, A plus C has to equal 10, right? But we can't just like count the numbers anymore because when A equals 10, this won't work because a digit has to go from 0 through 9, so this is only 9 cases. Okay, and then now we have case 6, B equals 6. A plus C equals 12. Now A can be 9, 8, 7, 6, all the way to 3, because when A is less than 3, then C will have to be 10 or more. So there's only 7 numbers here. Do you guys see that? Okay, and then we can just continue on for case 7, B equals 7, and then that means that A plus C equals 14. We can have 9 and 5, 8 and 6, 7, 7, 6, 8, and 5, 9. So that's only 5. So we can see that we went up and now we're going back down. So case 8, B equals 8. A plus C equals 16, 9, 7, 8, 8, 7, 9. So there's only 3 values. And then lastly, case 9, B equals 9. A plus C equals 18, and it has to be 9, 9, so there's only 1. So when we add this up, we have 2 plus 4 plus 6 plus 8 plus 9 plus 7 plus 5 plus 3 plus 1. And then when we add this up, it would be equal to 45. So that's our answer. Do you guys? Oh, wait, how long was I unmuted? Do you guys need me to go over that? I didn't realize I was muted. Wait, do you guys need me to go over it? Or is it okay? Oh, okay, it's fine. Okay. I think yes, we can do it like in a simpler way, but this was just to like show you the different ways you can use casework to like solve problems. Okay, so I think you guys were good with this. Okay, so now we can go on to number 3. The product of the digits of 3, 2, 1, 4 is 24, and how many distinct 4-digit positive integers with unit digit not equal to 1 are there such that the product of the digits equals 18? And then we can give you guys a couple minutes to think about it. Okay, so we can start now. So first, let's take the prime factorization of 18. And this is equal to 3 squared times 2, right? So then we want all the cases where the 4 digits multiply to 18. So we can have case 1 is 1, 1, 2, and 9, right? And then the number of ways to order this is 4 factorial over 2, because we can order it in 4 factorial ways, but then we have to divide by 2 because 2 of the digits are the same. So this is 12. And then case 2, we can have 1, 1, 3, and 6. And then again, this is like the same number, so it would be 12 ways. And then lastly, we have case 3, we can have 1, 2, 3, 3. And then the number of ways we can order this is again 4 factorial over 2 because the 3s are the same, so this is 12. And then if we oh wait, give me a minute. We need to subtract the cases where the units digit is 1. So actually this is not 12 because we cannot have the units digit as 1, so we have to have the units digit as 2 or 9. And then to multiply the rest of them, there's 3 ways, so it's 3 times 2 is 6. And then here we have to divide by 2 again, which is 6. And then here we have we cannot have the last digit as a 1, so we can have the last digit as so we can put the number the 1 in one of the first 3 digits, so that's 3 times 2 times, and then 2, 3, 3. This can be ordered in 3 ways, so that's another 3, so that's 9. So 6 plus 6 plus 9 equals 21. Okay, so you guys asked what Alcumus was. Alcumus is just like a resource on AOPS where they give you questions and you can have the questions in separate topics like casework or complementary counting, or like I think they also have probability in there. So they have like a wide range of topics, and then you can and they give you questions for you to like advance in each topic. Okay, so you guys understood this? Do you guys have any questions about this one? Oh, okay, so I didn't forget the units digit could equal 2. So when we look at this, we have 2, 3, and 3, right? 2, 3, and 3, and we can order this in 3 ways because we can order it in a total of 6 ways, but then the 3s are like the same number. So we have to divide it by 2 factorial. Wait, I'm sorry, this should be a 3. 3 factorial over 2 factorial, which is 3. So this like accounts for 3, 2, 3, and 3, 3, 2. Does that make sense? Okay, so no questions. Here, we can go over this question next. 5 people are sitting around a round table. Let X be the number of people sitting next to at least one woman, and Y be the number of people sitting next to at least one man. How many possible values of the ordered pair XY are there? For example, 5, 0 is the result if all 5 people are women. And then I'll give you guys a couple seconds to like think about this problem. Okay, we can start now. So let's start with our case 1 again, which can be when all 5 people are women. The problem statement already gives us the answer. It's 5, 0. But let's like try to think about this by ourselves. So if we have all 5 women, they're all women, all denote, like all keep the women blue. We can say that looking at each of the people, the people next to them are all blue, so everyone is seated next to women. So there's 5 women, 5 people seated next to women, and 0 people seated next to men because there's no men at the table. And then case 2, we can have 4 women and 1 man. So we can have 4 women at this table, and let's say that like men are green, so there's 1 man. Now to count the number of women at the table, of people sitting next, to count the number of people seated next to a woman, we have that the 1 man is seated next to 2 women. The women to the left and right of the men are also seated to 1 woman. So, and then the people that are 2 away from the man are also seated next to 2 women. So that means that everyone is seated next to a woman. Now for the people seated next to a man, it's only the people to the right and to the left of the man. So it's 5, 2. And then case 3, we have 3 women and 2 men. So there's 2 ways to do this. We can first have the 2 men sitting next to each other. Here we have everyone is seated next to a woman again. And then we have 4 people seated next to a man. However, we can also have this as men seated apart from each other, like this. And then here, the people seated next to a woman are only 4 because the women sitting between the 2 men don't sit next to a woman. And then the people seated next to a man are 1, 2, 3. Are the women. Only the women are seated next to the men because the men are surrounded by women. Oh, you didn't guess case 2. Okay, let's go revisit case 2. So let me draw like a larger diagram here. So we have 1 woman, 2 women, 3 women, 4 women, and 1 man. So if we label this as women 1, women 2, women 3, women 4, and man 1. So when we look at the people seated next to a woman, we can first take in this woman. Woman number 1 is seated next to woman number 2, so it's sitting next to a woman. Woman number 2 is seated next to woman number 1 and woman number 3. Woman number 3 is seated next to woman number 4 and woman number 2. And then woman number 4 is seated next to woman number 3, so they're all seated next to women. And then man 1 is also seated next to woman number 1 and woman number 4, so he's also seated next to a woman. So everyone is seated next to a woman. And then for the people seated next to a man, woman number 1 is seated next to man 1. And then woman number 2 is not seated next to any men because the 2 people beside her are both women, so she doesn't work. And then number 3 is basically the same thing by symmetry. So only women number 1 and women number 4 are seated next to women. Does that make sense? Yes, we're getting to case 4, which is 2 women and 3 men. Here, I'll erase this diagram because we don't need it anymore. Okay, case 4. 2 women and 3 men. Now, when we look at this case, this looks suspiciously like this case, right? Because it's basically the women and the men switched, so then we can basically show that it's the numbers switched, right? Because in every, look at our first diagram here. If we take it so that the women are now green and the men are now blue, it's basically what we had here, but reverse, right? So then cases 4 to 6 are basically these cases flipped. Does that make sense? Yes, and then we can have case 5 is, well, yes, you guys are getting the cases are correct. And then the cases are the same but reversed. You guys are all very smart. Okay, so if we disregard case 4, 5, and 6, we can look at case 1, 2, and 3. Here's 1, and here's 2. So there's a total of 4. And then by what we just said, we can prove that it's 1, if we have 1 woman and 0 women, we can see that it's basically the same thing but reversed, right? So then if there's 4 on this side, there's also 4 on this side. So 4 plus 4 equals 8. So we're done. The answer is 8. Do you guys understand that, or you guys need some extra time? Do you guys have any questions? Okay, so no questions. Now we can look at number 5. I have 2 hats. In one hat are balls numbered 1 through 15, and the other hat are balls numbered 16 through 25. I first choose a hat, then from that hat I choose 3 balls without replacing the balls between selections. How many different order selections of 3 balls are there? And I'll just give you like a couple seconds to think about it. Okay, so let's start. So we can have case 1 is we choose the first hat. In case 2 is we choose the second hat. Okay, so when we look at case 1, we have the hats. We have the hat with balls ordered 1 through 15. So there's 15 total balls, right? And then we want to choose 3 balls without replacing the balls between selections. And we want how many different ordered selections. So we want like the order of the balls to be specific. So we can have 3 balls. For the first ball, we can choose any of the 15 balls in the hat. So that's 15, right? And then for the second ball, we need to choose between the 14 balls that are left after this ball was taken out. Like, let's call this ball A. We have to choose between the 15 balls except for ball A, so there's 14 balls. And then using the same logic, let's say that this one was B, we can choose from the 15 balls except for ball A and ball B, so that's 13. And then pulling out our calculator, or like you can multiply by hand, but for the sake of time, we'll just use our calculator to find that this is 2370. Okay, and then the second hat is 16 through 25. So to count the number of numbers between 16 and 25, we can see that there are 25 total balls, and then 15 were in the first hat. So 25 minus 15 equals 10. So there's 10 balls here. Okay, so we can use the same logic as in case 1. For the first ball, we have 10 options. And for the second ball, we have 9 options. And for the last ball, we have 8 options. This is 720 total ordered selections of the 3 balls. And when we add these together, this is equal to 3450. So 3,450 total ordered ways. See, this one was a nice, like, relatively, nice problem. I'm pretty sure it's 2,730, but yeah, I think it's 2,730. Okay, so we'll be moving on. Actually, it's 3:29. Do you guys want like a break for a minute? Okay, so we can just give you guys a break. Oh, actually, yeah, we'll just give you guys like a break for like 2 minutes, and then we can come back at 3:32. Okay guys, break time is over and we can move on to number 6. Okay, so an old billionaire is writing his will and deciding how to distribute his 9 mansions among his 3 children. He wants to give each child at least 1 mansion, and he does not want to give any 2 of his children the same number of mansions. In how many possible ways can he distribute his mansions? Okay, so looking at this problem, it seems that we're going to have to be doing casework on how many mansions each child receives, right? So you can go case 1. Let's say the first child receives 1 mansion, and then we can't have the second child also receiving 1 mansion because every child has to have a different number of mansions. So we can say that the second child will receive 2, and then this leaves that the last child with 6 mansions. And then case 2, let's say that we have we can say that the first child has one mansion, and then the second child can have like 3 mansions, right? And then this leaves the last child with 5 mansions. Now we can't have 1 mansion, 4 mansion, and 4 mansions because like the 4s are repeated. So we can go to case 3. We'll have 2 mansions plus 3 mansions plus 4 mansions. So these are our 3 cases because if we go to the next step, like 3, 3, 3, all the numbers are the same, so that's impossible. So now let's start with the first one. We need to decide how to distribute the mansions. Let's say that we have mansions A, B, C, D, E, F, G, H, and I, right? So we want the first, we can order this in a way that has, this belongs to the first one, this belongs to the second child, and this belongs to the third child. So we can order it in a way so that the total number of orderings is 9 factorial because we can order the 9 mansions in any way. And then here we have 2 mansions, right? And then we have to divide by 2 factorial because we can order the 2 mansions in 2 factorial ways. And then we have to divide by 6 factorial because like D, E, F, G, H, I is the same as D, F, E, G, H, I, or because the child is receiving the mansions anyways, and it doesn't matter what order it's in. So it's 9 factorial over 2 factorial times 6 factorial. Oh, and times 1 factorial, I guess, for the A, but that doesn't really matter. And then for the second case, we have, again, 9 factorial ways, and then 1 factorial ways times 3 factorial ways times 5 factorial ways, right? So you guys see, like, how we did that? And then the third case is 9 factorial over 2 factorial over 3 factorial and 4 factorial, right? And then when we pull out our calculator again to look at this, let's see, what is it? Okay, so the first one is 252. The second one is is 504, and then the third one is 1,260, I think. So then if we add this up, we get 2016. Okay, so we have 2016. However, we're not done yet because we assumed that we didn't order the children yet. We just have, like, we order the numbers from least to greatest. But when we have 1, 2, 6, it can actually be written as 1, 6, 2 or 2, 1, 6 and so on. So there's 3 factorial ways to order them, right? So you have to multiply 2016 by 3 factorial because we need to order the children in each of our cases. And then this ends up with 12,096, I think. The calculation is not the important part. We just need to understand the methods of solving it. So is this good for you guys? Do you guys have any questions? Okay, so I think that's, is there a factorial button on the calculator? I mean, I'm not like an expert on calculators or anything, but if you have a TI-84, like a TI Inspire, I'm pretty sure you can quickly find the factorial button once you play around with your calculator. Okay, so I think we're done with this problem, and then we can go on to the next problem. So now we have a nice pretty diagram, and how many different rectangles can be formed by connecting 4 of the dots in a 4x4 square array of dots in the figure 2.10 such that the sides of the rectangle are parallel to the sides of the grid? And then I'll just give you a couple seconds to think about it while I answer some questions. Oh, the answer to number 6 was 12,096. 12096. Figure 2.10 is just the figure that is shown here. Yeah, just like ignore the number. Okay, so let's start. Our first case will be, whoops. Okay, so our first case will be the smallest rectangle that we can have, which is just this rectangle, right? So we need to find the number of rectangles of this size in the grid. Then we can just quickly draw them to see that 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, right? So for the first case, there's 9. And then if we want, now if we want to find our second rectangle. Let's say that it's this size, right? This is the second smallest rectangle. And then when we're looking at it, we are trying to find, like, count the number of rectangles that appear in this. And then if we want it to be horizontal, we can see that there's 1, 2 per row, right? And then since there's 3 rows, there's 6 rows that are there's 6 that are horizontal, right? And then we can also count the vertical one, so that's times 2, so that's 12 total. And then for case 3, we can have the long rectangle, and then there's 1 for each row, so there's 3 horizontal ones, and then if we multiply it by 2, there's 3 times 2 equals 6. And then our case 4 is equal to this triangle. I mean, sorry, not triangle, this rectangle. And then if we want to count it, we have 1, 2, 3, and 4, right? So case 4 is 4. And then our 5th case is when we have our rectangle that is 2 by 3. When it's horizontal, we can have 1, 2 horizontal ones. So it's 2 times 2 equals 4. And then our last case is the big square, and there's only one of them. So when you add them up, you can get let's see, 9 plus 12 plus 6 plus 4 plus 4 plus 1 equals 36. So there's 36 total rectangles. So do you guys have any questions? Okay, we cannot have like diagonal triangles or like the diamonds or something. Like, you guys are talking about like this, right? This doesn't work because we want the sides of the rectangles that are parallel to the sides of the grids, and then this is like not parallel to this side, so it doesn't work. But yeah, that was smart. We can count squares because like squares are technically rectangles. Okay, so you guys want me to go over this again, but a little bit slower? Okay, I guess we can just spend a little more time on this problem. So our first case is these small triangles, right? And if we count them, there's a total of 9 of these small triangles, right? And then we can just draw all of them in. So there's 9, right? And then let's say that we have the next triangle is the 1 by 2. I say that this is 1 by 2, not 2 by 3, because I'm looking at the length, not the number of dots that like it has. So this is 1 length, and this is 2 lengths, so it's 1 by 2. So here's 1, and then here's 1. So there's like 6 that are, wait, this is not really easy to see visually, so let me redraw them. So we have this one, and then we have this one, and this one, and so on, right? So there's 6 of them that are horizontal. And then I'm saying that we can multiply by 2 because we can also have them vertical, which is basically our first drawing just flipped over. So there's also 6 on this side. So there's 6 on both sides. So do you guys understand why I multiplied by 2? Oh, I keep on saying triangles. I'm sorry. Yes, this question is possible without casework. But we're like not. Today we're focusing on casework, so we used casework to solve this problem. Okay, so do you guys need to continue with the rest of it, or are you guys good? Do you guys have any more questions? Are squares counted as rectangles? Yes, because I think we learned we learned in geometry that squares are technically rectangles, but not all rectangles are squares. Okay, so where can we view the recorded classes? I think if you go on to the Kid Teach Kid website, you can find it, or you can ask Rich or something, because I'm not like in charge here. Okay, so I think we're done here. And then we can go on to the next problem. In how many ways can you spell the word noon in the grid above? You can start on any letter, then on each step you can move one letter in any direction, up, down, left, right, or diagonal. You cannot visit the same letter twice. And then I'll just give you a couple seconds to think about it while I answer some more questions. Okay, so let's start. So when we're looking at this, when we want to spell N, we need to start on an, when we want to spell noon, we want to start on an N, like here, or we can start on an N like here, or we can start on an N like here. So it's the corners versus the sides. So we can do case 1 is corners. So if we start on a corner here, we want, since it's noon, we want to go from an N to an O, right? But there's only one way to do it, which is to go diagonally to this O. So there's only one way to do it. So it's 1 times. And then from this O, we need to go to another O, right? And here we have 3 directions. We can either go here, here, or here. So there's 3 O's that we can land up on. And say that we land up on this O. Now we need to go to an N. And we can go diagonally this way, horizontally diagonally, vertically, or diagonally. So there's 5 ways, 5 ends that it can end up on, so there's 15. But also we have 4 corners, like this case is just starting from this corner. And we have 4 of these corners, so we can have 4 times 15, which is 60. Is that good? Okay, and then for case 2, we can have the sides. Let's use a different color. Let's say that we start on this end, right? When we want to go to an O, we can either go this way, which is like horizontally, or we can go here, which is diagonally. So there's 2 O's that you can end up on. And then when we have an O, we need to go to another O, right? Which is the same as in this case. So there's 3 O's we can go to. And then lastly, when we have an O, we need to go to an N, so it's like 5 cases by what we did in the previous case. And then 2 times 3 times 5 is 30. And then since we have oh wait, okay, class is ending soon, so that's okay. I have some problems that we didn't get to, but we'll just finish this problem first. So we have oh, and we cannot visit the same letter twice. Okay, so when we have 30, and then 30 times 4, well, I mean not 4, 30 times 8 is 240. And then when we add these together, we have 300. However, we cannot visit the same letter twice, so we need to subtract those cases. This is technically overcounting, but like we can use it in our casework class today. So one way to go is N to O to O to N, right? And that's like impossible. We can't do that. So there's, wait here, let me, whoops. Huh. Wait, give me a moment. My pen is malfunctioning again. I don't know why this keeps on happening. Okay, so we can go from N to O, and then back to the same N. And then this is a cycle that's going this way, but then we can also have the cycle going that way, right? So there's like 2, so there's 2 times the number of ends this could happen to, and this can only happen to the side ends, because when we have a diagonal end, it starts and then it goes away from that end. So there's 8 of these side ends, so there's 16 like ways that we overcounted. So 300 minus 16 is 284. So that's our final answer. Do you guys have any questions? Okay, you don't understand the overcounting. So basically we counted the ways where we start from an N and then go to an O and then go to a different O and then go back to an N. But then in doing so, we also counted the cases where we went from an N to an O and back to the same N, which is impossible because we can't visit the same letter twice. So we needed to subtract the cases that didn't work that we counted. Does that sound good for you? Okay, so you're saying that we overcounted 8 and not 16. But like, let's say if we start at this n, we can go to this O, to this O, to this n, right? Okay, let me erase this unnecessary stuff. But also, like, instead of going to the O, like next to it, we could have gone diagonally and then go to this O and then go back to this n, right? So there's like 2 ways the cycles could have gone. So then 2 times 18 is 16. I mean, 2 times 8 is 16. Okay, so I think we can end class here and then I'll give host to Andy. We had 2 more problems to go to, but that's okay.